So we are studying absolute convergence and conditional convergence for alternating series. So last time we saw, so let's uh, review quickly the process of testing for them. So we have an alternating series given to us. So in step 1, we are going to use alternating series test on the given series. Now, if it is convergent, then we go to step 2. If it is divergent, then obviously there's nothing more to do. So one would stop and say that the series diverges. So if the alternating series was convergent, then we would come here. So now we're going to take the absolute series. So that means forget about alternating signs, just take the absolute value. And now we will apply the earlier convergence tests, the ones that we studied in the previous sections. Now, if this absolute series is convergent, then we say that the alternating series that we started with is absolutely convergent. If the absolute series is divergent, then the alternating series that was given to us is called conditionally convergent. So let's practice this idea with the following example. So here is an alternating series, and we will first apply alternating series test. So this is our step 1. But if you look at the series, you will notice that we did this earlier as example 2 when we were studying alternating series. And so you can go back and check on it, and we found that this alternating series is convergent. So if you go back few pages, you will find it. So therefore, since it's convergent, we will go to step 2. So we're going to step 2. So in step 2, we take the absolute series So absolute series means we're going to take the absolute values of AK, which means drop the alternating signs, and we are left with K over K squared minus 1. So now we have to test this series for convergence. Okay, so if you think about it for a few seconds, you will realize the most efficient way would be to use limit comparison test. Because this has a rational expression as its terms. So since we have rational expressions, we should use limit comparison test. You can look at your table of convergence tests to recall what this test was. So my AK is K over K squared minus 1. I'm just calling it AK instead of absolute value of AK because it's after all an independent separate test that we are running, so I could call this AK. Now remember, I have to choose a BK. So BK would be the rational expression which has the net power. So the power of this polynomial is 1, of this it is 2, so the net one is 1, so I'm going to use 1 over k. Okay, so now I have to take the ratio and find the limit k going to infinity. So ak over bk. So that's pretty straightforward. You have k over k squared minus 1 times k over 1. So that gives me this. I would divide by k squared. And that would be 1 over 1 minus 1 over k squared. Now as k goes to infinity, this clearly goes to 1. It's 1 over 1 minus 0, so that is 1. Okay, so since this limit is, so this is my L, and this is between 0 and 1, therefore series AK and BK go together. But series BK is diverging, therefore the series AK is diverging. So therefore the absolute series is divergent. So therefore the final conclusion would be the alternating series is conditionally convergent. And the reason is because the alternating series converged. So the alternating series converged, but the absolute series diverged. Therefore, the alternating series was conditionally convergent. Okay, let's continue with the next example. So we are looking at this example. So again, it's an alternating series. So step 1, we are going to use the alternating series test. Okay, so this test consists of two parts, two tests. So test 1 is to check if the limit of the terms AK is 0. So you have to check whether it is 0. So let's start limit k going to infinity, k over ln k. So first thing is remember that AK is k over ln k when we are doing the alternating series test. So this is infinity over infinity form. Therefore, we're going to have to use the L'Hopital's rule. So we can write it as x over ln of x. So if you're going to take derivatives, we should not be writing it as functions of k. We have to go to the continuous function form. So Now we apply the LH rule. So derivative of x is 1 and derivative of 1 over x is 1 over x. So this is equal to x, and this goes to infinity. So therefore limit k going to infinity, k over ln k is infinity. So which is obviously not equal to 0. Therefore test 1 fails. So if test 1 fails, the alternating series test tells us that the alternating series that we started with is diverging, so diverges. So we stop here, there's nothing more to test, and the conclusion is that the alternating series that we have here is divergent. Okay, let's go to the final example. Well, we have two more. So let's look at one more. So this is an alternating series. So again, step 1, we're going to start with alternating series test. But if you look at this series, you will notice that we did the alternating series test in example 3 earlier. So again, you can scroll back and check, and we showed that this series converges. So this series converges. So therefore it makes sense to go to step 2. So we go to step 2. So in step 2, we're going to take the absolute series and test for its convergence. So test. So we're going to test the absolute series. So what is the absolute series? It is summation ln k over k. So how do we test the series of this kind? Now, some of you may remember that we actually did see it. So the most convenient way to do it would be to use the direct comparison test. You could also use the integral test in this case. So you could also use so we're going to use the direct comparison test. So you have ln k over k, and in this case you can easily see that you can bound it from below by 1 over k, because 1 is definitely less than ln k, so you get the lower series. So this is what I'm going to choose as my bk, this is my ak, and my choice of bk, the series diverges. So since this guy diverges, therefore we can say that the series AK, the one on this side, also diverges. So now we have our conclusion. So we have the absolute series diverging, and the alternating series was converging. So the overall conclusion is that the alternating series, the one that was given, is conditionally convergent. Okay, let's continue with the next and the last example. So again, we have an alternating series. So step 1, we try the alternating series test. So first thing is, let's pick out our AK, which is k over 2 raised to the power k. So test 1 is to check the limit of AK, which means k over 2 raised to the power k. What is it? Well, you clearly have infinity over infinity, so we would use the L'Hopital's rule. So let's write it as x over 2 raised to the power x. So derivative of x is 1, derivative of 2 raised to the power x is 2x, 2 raised to the power x times ln 2, and as x goes to infinity, this obviously goes to 0. So therefore, limit ak is 0. So that is good. Yes. Now we have to move on to test 2. Now for test 2, we have to show that it is a non-increasing sequence. So the terms ak plus 1 is less than equal to ak. So ak plus 1 would be k plus 1 over 2 raised to the power k plus 1. And is it less than k over 2 raised to the power k? Well, in this case, it's simple algebra. So you could say 2k, so I'm cross multiplying, is less than equal to 2 raised to the power k plus 1 times k. So 2 raised to the power k and 2 raised to the power k can cancel on both sides. You'll be left with one term of 2. So this is k plus 1 less than equal to 2 times k. So that means negative k plus 1 is less than equal to 0. So I'm moving it on this side. So yeah, sure, that is not a problem. Negative k is definitely going to be more than plus 1, so this will be a negative term. So therefore, the alternating series converges. So therefore, alternating series converges, and so we go to step 2. Now in step 2, we test the absolute version. So the absolute series in this case is obviously k over 2 raised to the power k. Now this is a classic ratio test problem, and I'm sure you've seen it somewhere before by now. So I'm going to take the ratio ak plus 1 over ak, which will give me k plus 1 over 2 raised to the power k plus 1, and then dividing by ak makes it 2 to the power k over k. So that is k plus 1 over k, collecting those two terms, and from here and here I'm left with a 2 in the denominator. So this is 1 plus 1 over k times 1 over 2, and as k goes to infinity, this clearly goes to half, which is less than 1. So therefore the absolute series converges. So here we have a situation where the alternating series converged, the absolute series also converged. Therefore the overall conclusion, the alternating series that was given converges absolutely. So we have absolute convergence here. So we have seen examples of conditional convergence, we have seen example of divergent sequences series, and now this was an example of an alternating series that converges absolutely.